So let's talk about vector spaces. In your book, there's a whole set of axioms that have to be satisfied to make up a vector space. I'm going to highlight a few of those here, but this is going to be just a little loose right now. So bear in mind that there are some more things, but the biggest things are that a vector space is a set of vectors. Now, when we're saying that these are vectors, what I really just mean is there's a set of things that we're going to call vectors. Okay? They don't have to look like regular vectors. They can look like other things. So sometimes those vectors are vectors. Right? So my primary example of vectors is vectors. That should not come as a huge surprise. Another thing that vectors might be is they might be numbers. Right? The real numbers are a kind of a vector space over themselves, right? Another example might be that they're matrices. So I might think about matrices as a vector space. And they might be functions, which maybe shouldn't come as a surprise because if I'm thinking about matrices as vectors, well, a matrix is a function, so maybe functions are also a viable consideration for vectors. Now, what the vectors are depend on the space that you're in. Does that make sense? Why is everyone just shutting off their cameras? It's just me and Jordan. All right, whatever. All right, Jordan. So, did this make sense?
I believe so.
Okay, good. I'm glad that the answer was that you believe so, because frankly, no, this shouldn't make sense, but it works. It is a little weird. All right, so I've got this set of vectors, so that's some stuff. And then there's going to be a couple operations. And I need at least two operations. I'm going to put at least here. Don't worry about why. There might be more operations, but two operations are going to be necessary. The two operations that are necessary are scalar multiplication and vector addition. You guys with me on that? And then I said I wasn't going to really write them down, but I decided that when I wrote down biggest things, I was sort of being unfair, so I am going to write all of them down. So the first thing first is that, let me do this. This is going to make my life a little easier if I say, assume x and y are arbitrary vectors and a and b are scalars. And I guess that I should say here that I am tending in this book to assume that we're talking about with scalars in the real numbers. Does that kind of make sense? I don't necessarily have to pick that, but I also don't want to overwhelm you all with the full generality of a vector space. So we're going to talk about vector spaces over R. Which really just means that the scalars that we're talking about are real numbers. Does that make sense? Another option that would be pretty valid here that I think you guys could handle is over C. So we could talk about a complex vector space. And in that case, we'd just be saying that the scalars are allowed to be complex numbers. All right. So I've got X and Y, there's vectors, A and B are scalars. The things that are going to need to be satisfied are X plus Y is going to need to be Y plus X. I need associativity, which is X plus Y plus, I guess I needed Z. So things are, addition is commutative, addition is associative. I need a zero vector. So what happens when you add the zero vector to things? So if you take
the same.
Good. So there should be a way to add, right, a vector that you can add to things and have those vectors stay the same, right? So there needs to be a unique zero vector. Please note, these, depending on the way that things are defined, the zero vector doesn't have to be a vector of all zeros. It just has to be the thing that when you add it to other stuff, they stay the same. I know it's hard to imagine that it could be anything else, but just please bear with me. It's real weird. We'll get there, I promise. But for right now, just like take this word of caution. It can be weirder than you think. Okay, so there's a unique zero vector. There are inverses. So for each vector x, there is a vector minus x with x plus minus x equals the zero vector. So everything has an additive opposite, right? Basically, negative numbers or negative vectors exist. The scalar 1 times the vector x is equal to the vector x.
Really quickly on 4, are you saying x plus negative x is equal to the zero vector, or is it like always like, I'm basically asking, like, does it have to be 0, or does it just have to cancel out? Like, does each entry need to be 0?
So the concept of entries is what's going to get us. Vectors don't all have to have entries. All the vectors we've dealt with so far have entries, and then we can think about, oh, okay, there's finitely many entries. When I kind of jam these two things together, all the entries cancel. Great. That's sort of the concept that we've been in. It is possible that we might be in a different place soon. And so what I'm saying is they have to add up to the zero vector that's referenced in number 3. Okay. So the 1 here, the meaning does not change. That is still 1 in the real numbers. Right? That's not like a new 1. That's the same old 1. All right. Thing 6 is c times x plus y. So if I take a scalar c and multiply it. Oh, and I guess I said a and b were going to be my scalars, and then I started using c because the book uses c. So I'm going to say C, C1, and C2, just to mimic I'm just trying to mimic exactly what it says in the book so you guys don't get confused if you look this up later. So what do you expect this multiplication to do?
Cx plus dy.
Yeah, you expect it to be able to distribute. Okay, so we're just going to require, oops, not Cx plus Cx, that would be weird. So this is scalar multiplication distributes over vector addition. Okay, and thing 7 here, rather. Ah, frick. Thing 7 is that one. Thing 6 is the one that I wanted. I'm sorry, guys. It's not as easy for you to move them around if you're taking notes, is it?
Does it matter the order?
No, all the things have to be true. I'm just trying to make it exactly what's in the book. So if I have C1 times C2 times X, what do I expect this to have to be? Probably expect that if you multiply a couple of scalars in a vector, it should be the same no matter what order you do it in, right? So this should have to be the same as C1 times C2 times X. And then my last thing is that if I take C1 plus C2 times X, that I should get C1X plus C2X. Okay. Now, there's a couple things that are hidden in here that aren't necessarily obvious that are the first things that you should check. So the first things that you should check are that X plus Y, right? If you take two vectors and add them together, that has to be in the space you're talking about. Another thing is that if I multiply by a scalar, that also has to be in the space that I'm talking about. Okay, now most of the time here, you're not going to have to check all of these things because most of the time we're going to be talking about what are called subspaces. So a subspace of a vector space is itself is a subset that is also a vector space. And this is going to get me to Jacob's initial question here. So in order to check whether something's a subspace, you can get away without checking a bunch of these things. The reason I can get away without checking a bunch of these things is that, frankly, these are mostly about the way vector addition and scalar multiplication work, right? So the ones that I'm really going to be concerned about are, is X plus Y still in there? Is Cx still in there? Does it have 0 in it? As long as those things are true, then I'm going to have a subspace because the rest of them are just about whether the operations play nice together. So in order to check for a subspace, I just need to check 3 things. And really, I only need to check 2, but the third one is so nice, I'm going to put it in here. It's actually a consequence of the first 2, but it's really easy to check first. So I'm going to kind of put that one down here as a first things first. You should really check this. Zero has to be in the subspace. If 0 is not in there, then it doesn't stand a chance in hell of being a subspace. The other two conditions that I need to check are X in the subspace and Y in the subspace implies that X plus Y is in the subspace. And that X in the subspace implies that CX is in the subspace. Subspace for any scalar C. You guys with me on this? All right, and I'm assuming you want some examples because this has been hella abstract, right? Yeah? All right, let's start with two really easy examples. Maybe three. Okay, so let me start really easy. Let me consider R3 is a vector space? Question mark? Okay, so is R3 a vector space? It really better be, right? If it's not, I probably need to revisit my definitions. Because I've been talking about it like it's a vector space this whole time. In fact, I'm sure I've used that word to refer to R3 before, right? I'm sure I've said three-dimensional vector space, right? Okay, so let's just check and make sure that all these things work. So we just go up to our list and we say, all right, so is vector addition commutative in R3? If I add two vectors, is that the same as if I add them in the other order? They need to go like tip to tail, right? That's that whole parallelogram picture we're always drawing, right? So, yep, one's true because of the way I defined it, right? The parallelogram picture is a thing. Is associativity true? Yeah, we've done that a bunch of times. You could get out the coordinates and work on it with the coordinates if you wanted to. What's the zero vector in R3?
0, 0, 0.
Yep, that's the vector with entries 0. So I might even just write that down here. Like notice. Right. So I'm just kind of running through this checklist, right? Actually, what the hell? Let me grab my whole checklist here. I'm just gonna scale this thing down and come on. Okay, it's not a really serious video game. All right, so check 1, check 2, check my zero vector. For every vector x, there's a vector minus x. Yeah, it's just -1 times it. Like, okay, I'm good with that. Is 1 times a vector equal to the vector? Yeah, that's how we defined it. You guys notice how this is kind of boring because most of these are just the definition. Okay. Is this how scalar multiplication works? Yeah, sure is. Is this how scalar multiplication and vector addition works? Yeah. And yeah, right? Okay, so I believe that we've checked that R3 is a vector space. And that was super boring. Okay, so let's check a different question. So is oh, I don't know, the set of vectors x and y with y equals x plus 2 a vector subspace. So in other words, I'm looking at vectors that look like this, x and x plus 2.
Where's the zero vector?
Good. Where's the zero vector? Is the zero vector in there?
Yeah.
Why? What's the zero vector in R2?
0, 0.
Okay, so your claim is that we can produce an x so that we get 0, 0, right? What x do you put in here to get 0, 0? Yeah, it'd have to be 0 and -2 at the same time, right? Okay, so really what I'm doing here, is I'm thinking like, okay, so this is the set of vectors that I'm talking about, and this 0, 0 is not in there. So what's going on here graphically, and this is a little bit easier to approach graphically, so if you can approach these graphically, do so. But what's going on here is I'm thinking about, this is R2, right? So here's R2. And I guess I should change my color here a little bit. Let's just go play. Okay, so here's kind of all of R2, right? What does this set look like? X's and Y's with Y equals X plus 2. What does Y equals X plus 2 look like in R2?
It's a line.
Good, it's a line. And it goes through up here. This is 2 high, right? And it has a slope of 1 for 1. So this is the subspace that I'm talking about. Now, where's the zero vector live in R2? So is the zero vector in the green thing? No. What does that mean? Well, that means that if I took a vector here, I don't know, like this one, this is the vector 0, 2, right? Notice that if you take the vector 0, 2 and add it to the vector 0, 2, what do you get?
Zero, 4?
Good, you get 0, 4. Now what's the problem? Well, shit, 0, 4 isn't one of these, right? The second coordinate isn't the first coordinate plus 2. You guys see that? So there are two vectors in here that when I add them up, they get out of it. So when I said you have to check these kind of two pink things, right? Like x plus y has to be a vector and cx has to be a vector. Well, this thing fails even that, right? Which is why the zero vector is not in it. You guys see that? That's kind of this first condition, right? If x is in the subspace and y is in the subspace, then x plus y should be in the subspace. Well, when I checked that with two vectors like 0, 2 in here, right, it got out of the subspace. Is this kind of making sense? So what's the ultimate answer to this one?
not in the subspace?
Not just not in the subspace, but this thing, right? This collection of vectors described is not a subspace. Are you good with that?
Could we do an example that is slightly more complicated than R3 that is a subspace?
Yeah, absolutely. So let's consider x's and y's with y equals 7x. Okay, so I'm asking the question, is this a subspace? And the this to which I'm referring, right, is in full generality the set of x's and y's with this as a subset of R2. So because it's in R2 and because R2 is a vector space, I can get away without checking all 8 things. I just need to check the 2 subspace things. So I'm going to go grab those quick. So this is my subspace definition. I'm going to plop that whole... Why did I not get to select it? Yeah, no, that's terrible. Don't do that, Joe. Bad idea. Okay. So, oops, that was also terrible. Let's try scaling the whole thing. I'm going to slide this over here so I can look at it. I want to make it a different color so I can tell it from the thing we're talking about. All right, so there's my definition of a subspace, right? So it needs to have kind of 3 things. I'm going to check the third one first because the third one's optional, but last time it let me quit real early, right? Okay, so I'm going to start with that one. Is 0 in this subspace? So the vectors I'm thinking about in here, right, look like x and 7x. So is the 0 vector a number and then 7 times the number?
For sure.
Okay, cool. All right, so I buy that I should put a check mark by 3. That one, again, you don't really actually need to check it. But boy, is it, right, it's like really an easy way to stop working on a problem. All right, so I need to check problem part 1 here, which is that it's closed under addition, right? So I need to take 2 arbitrary vectors in my subspace and then show that x plus y is in my subspace. So I'm going to say, I'm going to let x be this one and y be a different one. How do I make another vector in this subspace?
Plug in a different x.
Yeah, I just need to plug in a different number. I'm going to plug in y. So I'm going to do y and 7y. Is it okay that I've used x with a hat on it for a vector and y with a hat on it as a vector, and then x and y as scalars? Does that make sense? Okay. That's the way my brain works here. I like to have that like, oh, x is just the scalar version of vector x. But if that twists your head off, don't feel like you have to use this notation. So I've just got 2 vectors, right? And I need to check whether x plus y is in the subspace. So I'm just going to think to myself, okay, so what's x plus y then? And if I'm doing completely proper notation, I should be saying, let x and y be this. And now let's consider x plus y. So x plus y is x and 7x plus y and 7y. And now the plus here that I'm using is the vector addition from R2, right? So how does that work?
The top row will be x plus y,
Good?
and the bottom row will be 7x plus 7y.
Good. Okay, and now I should see that that's a thing on the top and 7 times that thing on the bottom. Do you guys see that?
Yeah.
Okay, you're already kind of with me. I'm going to make that really explicit and say on the top it's x plus y, and on the bottom it is 7 times the quantity x plus y. And my claim then is that this is in this set of vectors, which I should have given a name. I'm going to call that S for subspace under consideration. Right? So this whole thing checks off property 1. You guys with me? Okay, how about checking off property 2? I need a vector to play with. So I'm going to say let x be x and 7x. Then what? What's the thing I'm supposed to be checking here? X is in the subspace implies that Cx is in the subspace for any C in R. So I guess I need an X and also a C. Oops, not a vector C, but just a C in R. All right, so I've just let X be this thing, let C be a number in R. Now, what's the thing I need to consider?
When we multiply that scalar, if the new, I guess, vector is within that vector space.
Perfect. Yep. So I need to consider C times X. Okay. So C times X is going to be, well, it's going to be C times X and 7X. And this is scalar multiplication in R2, right? And I know how scalar multiplication in R2 works. What am I going to get?
Cx and 7cx.
Okay, and I'm going to rearrange that just slightly because I think that it's most obvious that I get C7x, right? And then I'm going to notice, like, okay, this stuff, this C, this 7, and this x, those are all 3 real numbers multiplied together, right? So the result of that is a real number, and multiplication in the real numbers is associative. So I can swap the 7 and the C, and then group, sorry, it's commutative, and it's also associative. So I can swap those around and group up a little differently. So I'm going to say I have Cx up here, and in the bottom I have 7 times Cx. And then I'm going to say this is a vector in S, and that means I can check off thing number 2. You guys good with this? Okay, so far I've given an example of something that very clearly was a vector space. I gave an example of a subspace or a subset of R2 that wasn't closed under either addition or scalar multiplication. And then here we have a subset that's closed under both scalar multiplication and vector addition. It should be noted that it doesn't have to break all the things. It could break just one or the other. Does that make sense?
Yep.
Can you guys come up with an example of a subset of R2 that would fail either one or two here, but not both? So what I'm asking for is a subset of R2 not closed under addition, and a subset, preferably a different subset of R2 not closed under scalar multiplication. Is it clear what I mean by closed? I've used that word several times here, but I'm not sure that I ever defined it.
I mean, we've used closed for like bounds and stuff.
Yeah, so this means, right, so being closed under vector addition means that if you add two vectors, you get a vector still. Right, so a subset is closed if adding any two things in it will keep you in it. So here I want a subset of R2 that's not closed under addition, but closed under scalar multiplication. Oops. And for this other one, I want a subset that's not closed under scalar multiplication, but is under vector addition. Do you guys want to spend a minute and try to conjure up a couple of those? The one that's something that's not closed under scalar multiplication but is closed under scalar addition is just a little bit hard to do, actually. Maybe. All right, I'm going to give you guys 4 minutes. Try to come up with one each of these two sets. Ready, set, go. All right, so Jordan says he may have solved our problems. What do you got, Jordan?
So for not closed under addition, wait, no. Okay, so what I have is x, y as a vector, and then y is equal to x squared.
Very nice. Okay. So that's essentially
I think it works for scalar multiplication, but it doesn't work for scalar addition.
So we think it works for scalar multiplication,
but not vector addition.
Okay, so I agree that it certainly doesn't work for vector addition, right? So to check whether something's closed, we're going to say, all right, so really we're talking about vectors with maybe just x and x squared with x and r, right? And this is a subset of R2. So if we're thinking about a vector x, that's x and x squared, and a vector y that's y and y squared. Okay, so if I look at x plus y, I'd get the vector x plus y, and on the bottom I'd get the vector x plus y and x squared plus y squared. And then your claim is that the top thing squared does not equal the bottom, so this is not in my set S. That's true. This is not closed under vector addition. Now, is it closed under scalar multiplication? How do you check scalar multiplication?
I just multiplied it by C, and I was like, you know, it looks like it's the same thing, but with a constant in front of it.
Okay, so you get CX and CX squared, right? Okay, now remember that the top thing squared has to be the bottom thing, right? So CX squared is not CX, except in the case of the zero vector. So you did come up with one that passes one of the three subspace checks, right? This thing contains the zero vector. So this is, in the end, we have not closed under either vector addition or scalar multiplication. And this is perfectly reasonable. The vast majority of subsets of the vast majority of subsets of any vector space are neither closed under addition nor are they closed under scalar multiplication. Most of them don't contain the zero vector. It just so happens that you found a nice one that does contain the zero vector but isn't closed under either operation. So this is not a subspace, but does contain the zero vector.
I must have spaced out for a second. Why do they have to be the same, the top and the bottom?
Oh, his definition was that it's something up top and then something squared in the second coordinate.
Yeah.
Mm-hmm. I'm confused, Jacob.
I'm confused too.
Okay. So when we multiplied by a scalar, right, we got CX.
Yeah.
So we got C times X and CX squared. The top coordinate squared is not the bottom coordinate. So this thing is not in S.
I think you forgot a squared there on your does not equal.
Oh, thank you. Does that make it more clear? Thank you, Cody.
No, I'm sure I'm just missing something super simple. I just don't.
So the subset of vectors that Jordan's considering, right, the ones he's put forward as a vector space,
Yeah.
they look like something and then that same something squared. And this vector here does not look like something and something squared because this something squared is not this thing.
Hmm.
Another way you could eyeball this is you could look at this. You could look at kind of the graph of what you're talking about. So you're talking about this parabola, right? Ish.
Oh, never mind. I see it. Okay.
And so this is a vector in that parabola. But if I scale it, right, which is what scalar multiplication does, so it comes off the parabola.
Mm-hmm.
So you can see that you're not going to be able to get very creative here, right? Because this is maybe our vector x and this is cx. So if it contains something, it has to contain all the scalar multiples of that thing.
Mm-hmm.
Right, so I'm going to be pretty limited to like stuff that's pretty friggin' flat. You guys see that? That's why these things on the front of the book are squares. They're rectangles. Because he's trying to clue you into the fact that they have to be subspaces, so they have to be flat. We'll talk about why they're subspaces in the next couple of days. But for right now, like, that's why they're flat. So did anybody else come up with a different example for these? So I need one that's closed under scalar I need one that's closed under vector addition, but not scalar multiplication. So here's my claim for that one. Let me see. I'm just gonna take this whole thing and just scoot it down a little ways. Okay, so one of these. Let me consider the subset of R2 that looks like X and 0 with X bigger than or equal to 0. So this is the right-hand side of the x-axis. You guys with me on that one? Is that going to be closed under addition? You're thinking about vectors that look like this, right? So if you take two vectors on the x-axis and add them together, they're going to be on the x-axis? Yep. If I take two vectors that look like this, is there a zero vector in here first? Yeah, the zero vector is when x is 0, right? It's the kind of furthest left-hand thing on the right-hand side of the x-axis. Okay, so I've got a 0 vector. Now, why is this thing not closed under scalar multiplication?
Because it can't be negative.
Yeah, if you multiply by a negative scalar, shit, you're supposed to get a negative vector, right? But it's not in the space. You guys see that? So, negative scalars. Right, so the negative scalars exist, ergo, this is not closed under scalar multiplication. How about one that's not closed under addition, but is closed under scalar multiplication? Let's see, this might be a little harder. Has anybody got a suggestion for me? Hearing nothing? What if I said the set of vectors x and y with x equals 0 or y equals 0? Right, this is the x-axis and the y-axis. Right, so I'm talking about these two lines, right? Okay, is the 0 vector in there? Yeah, certainly. Right, because that one's in there for two different reasons, right? Because x is 0 and y is 0, which is stronger than when x or y is 0. Okay, so I got the 0 vector. Is it closed under scalar multiplication? So if you take a vector that's on the x-axis and multiply by a scalar, is it still going to be on the x-axis?
Yeah.
Yeah. What about a vector on the y-axis?
Mm-hmm.
That works too.
Yep, also works. Okay, so I think I'm closed under scalar multiplication for that reason. We could write down coordinates and check. Really, it amounts to, something times 0 is 0. What about addition, though? What happens if I add those two vectors that I've drawn together? Yeah, you get one that's off the axis, right? If you add these two vectors together, you get this guy. That one's not in my subspace. Oops. Outside. Right, so this thing's closed under scalar multiplication, but not closed under vector addition. Is this making some sense, guys?
Yeah.
Okay, I'm a couple minutes over. Jacob, in answer to your question, yes,
Yeah.
it is okay that it might contain too many vectors.
So I figured that out pretty quickly, and then I moved on to the next parts of 10, and I quickly
Okay.
realized I knew absolutely nothing. So I'll ask about that next week.
Perfect. Yeah, looking at these problems and feeling like you don't know any damn thing is really probably a good place to start. I would much rather have you start this section underconfident rather than over.
Well,
Because
it succeeded in that. So.
yeah, this section is really, really abstract because we're going to start talking about what if vectors are functions? What if instead of adding vectors we did something else? Right? And it gets a little head twisty. I fully expect this set of problems to have some like serious confusion. So when you get confused, shout at me. Cool.
Mm-hmm.
All right. Good work today, guys.